All right. All right, very good. So those are the 4 basic transformations that we will encounter. And matrices is intertwined with those transformations. So in today's session, we will see exactly how that is. And at the end of the session, I want you guys to be able to perform operations using matrices and transformation as well. So to begin our session, we have a few operations here. Now, the first one is addition of matrices. The next one, scalar multiplication. And the last one is just multiplication of matrices. Now, I need you to take, let's say, 5 minutes to attempt these questions. So in the next 5 minutes, we'll take some solutions for these matrices. The first two should take you about 30 seconds to do. The last one is a bit tougher. So go ahead.
And I want to remind the students that for this session, you will need to have your writing implements as well as your books. All right, because we want you to participate in the session. You should leave here understanding what this topic is all about. So ensure that you're participating. All right, don't just come and sit and watch. You have to participate.
All right, so we're ready to take some answers. Now for the first one, what type of matrices are we adding together? Nobody knows?
For those who want to answer, you can just raise your hand and we'll unmute you. All right, so if you want to speak, just raise your hand.
So what type of matrix do we have here, or matrices rather? All right, so I'll just inform you of this one. So later in the session, when I ask again, you should know. So we have a 2 by 3 plus a 2 by 3. So we say row by column to get our matrices. Now, I saw someone post in the chat the answer for the first one. Well, and the second one. So they said 2. Let me get my pen. It's not allowing me to write, actually.
Let me see what is happening.
Right, so
Are you able to write now?
Yeah, I'm able to write. So the person said 2, 4. What was it? 2, 4, 5. And negative
2, 4, 5, negative 1, 2, 5. I'm assuming that should be in the second row. And for the second one, she has, that's Gabriel, 10, 4, 0, 2, 12, 2.
All right, so those are her guesses. So what about the last one?
I am almost sure I saw an answer right. So for the last one, it's 1, 3, 4, negative 2, negative 5, negative 8. And that's from Gabriel.
All right, so does everyone agree with these answers?
You can type in the chat, students. Please type. Let us know what you're thinking.
All right, so seeing that this is the introductory activity and I don't want to spend too long on it, this is just a quick recap for the matrix operations. So the first one, the response that we got was 245, negative 125. And it corresponds with what we have here, 245, negative 125. So very good, Gabriel. The second one, 1040 to 12.2 corresponds as well. So those two are correct. Now, let's see what the last one is. And that one as well is correct. So this indicates that you have prior understanding of operations involving matrices. So we don't need to spend much time to recap the various operations. Because what our focus is on the translation of, well, translation, rotation, reflection, enlargement of various objects given the matrix. Now, the aim of this session, as I've stated, is to use matrices to transform a plane figure and to determine the 2x2 matrix associated with each type of transformation. Now, our vocabulary, which we will encounter for this session, are translation matrix, enlargement matrix, reflection matrix, and rotation matrix. Now, let's quickly recall, how do we translate a polygon? Can anyone tell me? So if you were here last week, you would have been a part of that session where we spent some time looking at the translation of various objects. So how do we translate a polygon? Any ideas? All right, so someone said using vectors. Any other suggestion? Go ahead, Gabriel.
By identify the translator translation vector to
Identifying.
determine the direction and the distance it's moved.
All right, so once again, vector comes up. So I can agree that we use a translation vector to move about a given plane. So someone else said by sliding the object, yes, we definitely slide the points across the Cartesian plane using the translation vector. So what can we recall about reflecting a polygon? Reflection. So go ahead, feel free to open your mics. All right, so reflecting it in a mirror line. Anything else? What can we say about the size and shape of the object that is being reflected?
It is flip.
The size or shape of the object?
The size doesn't change and the distance between them is the same.
So the distance between the object, the image, and the mirror line. So the mirror line would be the central distance between the object and the image. Now the size does not change. So it stays the same shape and size. However, the orientation might look a little bit different based on how you look at it. All right, so next up we have enlarge a polygon. How do we enlarge a polygon? What is the most important word that comes up when we talk about enlarging a polygon?
Center of enlargement.
Yes, and another important word.
The scale factor.
Yes, so both of those words oftentimes comes up when we are focusing on enlarging a polygon. So does the polygon stay the same size?
No.
Does it maintain the shape?
Yes.
Okay, good. So it stays the same shape, however, the size changes based on the scale factor given. Now, lastly, we want to look at rotation. What can we say about rotation?
The shape remains the same, but the direction changes.
So this affects the orientation of the object. All right, so very good. And the first thing is to identify what we will be using when performing these transformations of our objects in matrices form. So transformation using matrices, polygons can be represented in matrix form. We simply place all of the coordinates of the vertices into one matrix. Now, this is called a vertex matrix. So earlier you mentioned translation vector. So don't get it confused. This now is called the vertex matrix. So this is what we will be using to perform various transformations. And it's not difficult. As you can see, based on the definition above, we're going to simply replace the coordinates of the vertices in one matrix. And we can identify the x and y coordinates, right? If we're given a point on the Cartesian plane, we can identify the x and y.
Sir.
Repeat. All right, so let's look at a triangle here. So this triangle has vertices A, B, and C. Now, what I want from you is now the definition said, to get the vertex matrix, all we need to do is to take the x and y coordinates and place them in a matrix. So I want you to give me the x coordinates. So look at ABC, and I want you to tell me the x coordinates of ABC. So let me just write it here, A, B, C. So give me the x coordinates first.
Negative
Negative 2, 0, and 1.
1.
All right, so give me the y coordinates.
Negative
Negative
1, 3, negative 2.
And negative 2.
Now, if we close this off, this right here is our vertex matrix, and it's that simple.
Oh.
So we simply need to read the coordinates of the triangle, and the x coordinates would go in the first row, while the y coordinates would go in the second row, as we did in the little demonstration just now. So getting the vertex matrix is pretty basic. Now, the idea is to be able to perform transformations on these vertex matrix. So finding the vertex matrix is one. However, performing the transformation is another story. But it's pretty much similar to performing the transformations without using the matrices. Now let's take a look at it. And the first one, translation vector. Now, a translation vector is a matrix used to translate coordinates on the coordinate plane, or as someone mentioned in the chat, slide in the object. So this translation vector will allow us to slide the object to various parts of the coordinate plane. And we want to take a look at this to see exactly what this is saying. This is just big words, and we want to put it in simpler terms by using some numbers to see exactly what this is saying. So let's look at this triangle. Triangle ABC has coordinates A being -2, 1, B 3, 2, and C 0, -3. Now, the first step, or the first part of this says, write the coordinates of the vertices of the triangle in matrix form. Now, if we're writing these coordinates in matrix form, what would that be? So give me the coordinates in matrix form.
Sir, for the top, you would have -2, 3, and 0.
Then,
And
One.
the
I can't see the other one.
2.
so it's up here.
And -3.
So this would represent the translation, this would represent the matrix form of the given triangle. So let's just put a little arrow, matrix form. Now, here's the tricky part. This says, determine the translation vector T if the image of triangle ABC has coordinates. Now, what is the image?
The reflection.
Well, in this case, what would it be? Seeing that we're focusing on translation.
Oh.
So our first transformation
Transition.
is translation. So what would the image represent? So the image, we want to know what this would represent. Because remember, they gave us...
Sir, the image would represent the new diagram like A1, B1, and C1.
Yes, definitely. So the image here is what we get after we've translated this triangle. So the question is that it wants us to find the translation vector T. So we're going to break this down a bit. So let's, I need to get another page here. So let me just add in another page quickly. All right, so everyone is on the blank page, right?
Yes, sir.
All right, we want to discover this together. So they gave us triangle ABC and it had coordinates. So let me just write the vertex, the matrix form of this triangle. So it was -2, 3, 0, 1, 2, -3. So let's say this is our object. This is our object or pre-image. So which one you prefer to use, object or pre-image?
Object, sir.
All right, so this is our object. So this is the vertex matrix of our object, right? And the question gave us the vertex matrix of the image. So after it undergoes the translation. So let me write that. So it is -5, 0, and -3. 5, 6, and 1. All right, so this is our image. And what happened is that this object went through a translation to get to this image. So remember, when we're translating an object, what do we do with the coordinates? So we have the translation vector. What do we do with the coordinates?
Define it
Yeah,
on.
add them.
So we add it. So if we were given the translation vector, we would simply add it to the coordinates to get the new thing, right? The image.
Okay, then.
That's what we would do, right?
Yes, sir.
Yes.
All right, so now if we want to move from the image to the object, because we don't know what the translation is, what operation would we do?
You will subtract the object from the image to get the translation.
Yes. So we would need to subtract the object from the image. So let's go. So let's write image first. -5, 0, -3, 5, 6, and 1. And let's subtract -2, 3, 0, 1, 2, -3. So what do we get when we do this?
It's -7, 3, -3, and 4, 4, -2.
Right, so check again. So remember, this is saying -5, take away -2.
Mhm.
-3.
So this is -3,
-3 again for the top box.
-3,
And -3 again.
-3. Down here,
4, 4, 3.
check the last one. It's 1. Take away -3.
-2 is the last one.
Check again. So it's 1. Take away -3.
4.
4. Now, what do we notice here?
Oh. The same value.
So all of row 1 is -3, right?
Yes, sir.
And
Yes,
all of
sir.
row 2 is 4. So this is saying that all the x values in our object were shifted by -3, and all the y values in our object were shifted by 4. So we can actually simplify this and write it as a so because it asked us for a translation vector, we can write it as -3 and 4. And this would be our t, and we get our marks and be on our way.
Okay.
So does everyone see what we just did?
Yes, sir.
So sometimes when you get these questions, you'd have to reverse engineer what is being done. So you'd have to look at the concept that is being applied to get to where we are and see what can be done to get back to what we want. So as stated, we have the object, we were given the coordinates of the image, and we know that we would need to add a translation vector. So now to get from the image to the object, we would then have to subtract. So this right here, let me just write what it represents. So this is the vertex matrix of the image. So let's say vertex matrix of the image, and this is the vertex matrix of the object. So we have to do a little reverse engineering there to get to our translation vector. All right, so let's see what comes next. Now, this is what we just did. Now they're giving us a visual representation of it. And as you can see, we actually did it without having any visual of it. So it's saying A prime, B prime, C prime, which is the image of ABC, has the coordinates, which were stated previously. And then the question is, what is the translation vector T? So we have the object in its vertex matrix. We have the image in its vertex matrix. Now, as we discovered, we would need to add a translation vector to get the image. Now, its basic transposition, we would transpose. So let's just use the starting letter of each of these. So let's say object is O. T represents our translation vector, and all of this represents I equals I. Now, if we want to get T by itself, we would need to transpose this O, right? And we know that when we transpose a positive, it would change sign to a negative. So T would now be equal to I minus O. So it's back to basic algebra in order to get our translation vector. So any questions there?
No, sir.
And as you can see here, it is represented as a column matrix or 2 by 1. Now, translation matrix. Now, a matrix that moves an object from one location to another on the coordinate plane, as we discovered previously. The matrix sum of a pre-image and a translation matrix gives the coordinates of the translated image. Now, the matrix sum of the pre-image and the translation matrix, that gives us the translated image. Now, let's look at that. So let's say we had -4, 2 as our translation vector or translation matrix rather. Well, in this case, we would refer to it as, let me just erase this. Let me put it as -4, 2, -4, 2. So let's say we have this as our translation matrix, and our object is 0, 1, 3, 4, -6, 7. So if this is our object, what would our image be? So this is a translation matrix. We have our object. What would the image be? So remember, in order to get the image, all we need to do is to add the object plus the translation vector or translation matrix in this case to get the new image. So what would that be if we're just adding?
-4,
So -4,
-1,
Yeah.
and -10.
-10 down here.
3,
3.
6,
And 9.
and 8. Oh,
So it's 7 here and 2 here. So it's that simple to get from the object to the image if we're already given the translation matrix or translation vector. And we can reverse engineer or go from the image to find the translation vector if needed. So we would simply need to subtract the object from the image to get our matrix. Now we have another example here. So triangle GHJ with coordinates G being 2, 4, H 3, 1, and J 1, -1 moves 3 units to the right and 1 unit down. We're required to find the coordinates of the vertices of the image, then graph and label the diagram. The translation matrix will have 3 in all entries in row 1. Why does it have 3 in all entries in row 1?
Mm.
Can anyone enlighten us here? Why does it have 3 in all entries in row 1?
Because the X values were shifted 3 times.
Yes, so all the X values in our image will be shifted by 3. And the same could be said about the -1 being the Y coordinates of our translation matrix, because all the Y coordinates in our image will be shifted by -1. And which direction do we go if we're moving by a negative in the Y coordinate?
Down.
Yes, because Y coordinate is up and down, X coordinate is left and right. All right, so before we move on to the next slide, can someone tell me the vertices of the image here if we apply this translation matrix to the coordinates given? So quickly, what are the coordinates? So let me just say image. Let's put our matrix here. What would our coordinates be?
There 5, 6, 4.
5, 6, 4.
Three,
0 and -2.
So does anyone else agree with this answer?
Yes, sir.
Does anyone not agree with this answer? Going once, twice, gone. All right, so let's take a look at what we have here. So as you can see, the translation matrix has been added to the object, which would then give us the image, and that is the exact matrix as what was given here. So very good. Miss Brian, you have past paper questions you could send to them, right? On matrix transformations in particular.
What we encourage them to do is to go online and look up for past papers, and they can actually find many different types of questions from those papers.
Okay,
So
good.
they can just go online and look at the past papers and do the questions from those.
All right, so that sums it up for translation matrix. Any question? Or translation of objects in matrix form. So any questions? So once you have the translation vector, you can simply represent it in translation matrix form and go ahead and apply. So in most cases, it's just, well, in most cases, it's just to add. And if you're moving from the image to try and find the translation vector, then you would need to subtract. So now we will be taking a look at enlargement matrix. And as stated earlier, for similar figures, the shapes is the same, but the size may be different. And corresponding angles are congruent and side lengths are proportional. So those are the basic characteristics of, well, there are two more. An enlargement or scaling is a transformation that changes the size of an object. And all of this was said earlier. Enlargement enlarges or reduces the object, resulting in a similar figure for the image. So when the center of enlargement is the origin, multiplying the coordinate matrix by the scalar gives the coordinates of the enlarged image. So coordinate matrix are in vertex form. So all enlargements assume that the origin is the center of enlargement. So that's in this case here. So remember how to multiply matrices, right?
Yes, sir.
Yes, sir.
All right, so we will be looking at some, well, multiplication will definitely take place a little bit down the line. So an enlargement is performed by multiplying the object positions, x, y, by the scale factor such that p prime is equal to s times p. Now, let's put some numbers to this. Now, let's say, well, an example here would be the scale factor being 3. So we have our image. This is the image. And this is the object. So when we multiply by the scale factor here, so the object times the scale factor would give us the image. And our scale factor is represented as a matrix. So whatever number we're given, so let's say we were given a scale factor of 2, we would have our matrix as 2, 0, 0, 2 to multiply our object. So that is how we go about writing our scale factor in matrix form. So we clear on that? An enlargement of matrices is it's one of the easier ones. Pretty much easier than translation because all you need to do is to find the scalar multiple of the given matrix. So let's look at some features of enlargement. So O is a center of enlargement or the origin as they stated to us. Now, if it has a scale factor which is greater than 1, what would happen?
It will be bigger, sir.
So we will get a larger image. So the image will be larger than the, so let me just put some jotting on this. So the pink ones are the object. So let me just put O. And these are the image. So if the scale factor is greater than 1, then the image will be larger than the object. If the scale factor is 0.5 here, so that's between 0 and 1, what would happen?
The image will get smaller, sir.
So the image would be smaller than the object. Now let's look at when it has a negative scale factor greater than 1. What happens here?
It going to turn upside down. A flip
Upside
inverse, sir.
down.
It flips.
So yes, there is a flip. And what about the size?
Oh, the size.
So this is the object in pink, and the yellow looking one over here is the image. So we said it's flipped, but what else? What other characteristics can we identify?
Sir, would it be negative?
What would be negative?
The image?
Not quite. I'm referring to the size, you know. What do you notice about the size?
It's no longer
Image is larger than the object.
Yes, the image is larger than the object. just as how here the scale factor, so let's say the scale factor is k, and if k is greater than 1, then the image here is greater than the object. Now down here, the scale factor, k, is less than -1. So that means the image would be bigger than the object. So what if we have a scale factor between -1? So k falls between, so it is less than -1. Wait, less than 0, greater than -1. Let me fix that. So this falls between -1 and 0. What happens? So this is the image.
The image is smaller.
The image is?
Smaller.
So the image is smaller. So these are a few characteristics that you will encounter. These are general characteristics from enlargement. These aren't specifically tied to matrices. Now, any value, whether negative or positive, can be used as a scale factor. If the scale factor k is less than 1, then the object moves closer to the origin. If the scale factor is greater than 1, then the object moves farther from the origin. So as you can see here, x here will represent our object, x prime here would represent the image. And as we can see, this is our origin point here. Let me just put OBJ and the image. So the object is all the way over here. And if it has a scale factor less than 1, then it is moving closer to the origin until it moves past the origin and then flips. So that is what happens when it becomes on the negative side. So let's review scale factor quickly. So if k, so k here is being referred to as the scale factor. So if k is greater than 1, the image is an enlarged, or it becomes greater in size. If k is between 0 and 1, the image is reduced. If k is equal to 1, the dilation is congruent transformation. So that means the size does not change, because it would be a 1-to-1 ratio where it is just the same as the object that is being enlarged. And if k is negative or less than 0, the enlargement takes place in the opposite direction from the center. So that is where we notice the flip, because it's taking place in the opposite direction from the center of enlargement on the same straight line containing the center and the object point. So let's look back quickly. So as you can see here, all the points, if connected to their image, so A to A prime would go through the origin, B to B prime would go through the origin, C to C prime through the origin as well. However, there's a flip as it starts to enlarge, because k is less than -1. All right, so we want to look at an example here using matrices to enlarge a figure. So we're given triangle ABC with coordinates A, 2, 3, B, 1, -2, and C, -3, 1. And we're required to enlarge by a scale factor of 2. So if we're enlarging by a scale factor of 2, what will happen here? What do you think will happen to the image?
It will get bigger, sir.
So it will be bigger than the object. But our aim is not to, well, we're required to graph it, yes, but we want to find the coordinates of the vertices of the image. So remember when I said enlargement is pretty basic in the sense that all we would need to do is to just find a scalar multiple. Do you recall what scalar multiple is of a vector or a matrix rather? So let's say we had a matrix 7, 4, 3, 8. And we wanted to multiply this by 3. What would happen? All right, so go ahead and work this. Give me a second. All right, so is everyone finished with this one? We want to multiply by 3. What would our result be?
21.
So 21.
9.
12.
9, 12.
12. 12 and 24.
24.
All right, so we're given this triangle. So back to this triangle, ABC. And we have the coordinates. So what we want to do is to put these coordinates in their vertex form. So when you put them in the vertex form, what do we get?
4.
2.
2.
So 2,
Negative
1 and negative 3.
3.
3, negative
3.
2 and 1.
Sir, wouldn't that be
2 and 1.
27 instead of 24?
we're here.
It's
Oh, is
8.
it? Oh, okay.
Yeah, it's 8. All right, so we have our object in vertex form. So now we want to, so this is the vertex form of our object. Now the factor of 2 is what we want to enlarge by. And a trick to note is when we're finding the enlargement or the enlarged matrix, all we would need to do is to use this number, whatever factor they give us, and just find the scalar multiple. So if we multiply this entire matrix by 2, what is our result?
2 2s 4.
So that's
4.
1's 2.
2.
2. Negative
3,
6.
Negative 6.
6.
6. Negative
Negative
4.
4. And 2.
And this would be our answer. So all right, so my question to you now is, so what if we got this to graph, right? So this is the object they gave us, and we plot this on our graph. So we did all of this. We use a scale factor of 2 to find the vertex form for the image. So this is the image. So what if we wanted to write this as our coordinates? How would we write it? So let's say A prime, B prime, C prime. What would we write? So A prime, B prime, C prime. What would we write?
4 2 for A prime.
What would A prime be?
4 6.
So 4, 6.
2 negative
B
4.
2 negative 4.
2, negative 4.
Negative 6 2.
So this now would be our image. And all we would need to do is to just plot this and our
Yeah.
question would be finished. So as you can see here, we multiplied each coordinate by 2, which is our scale factor. So as we did on the previous page, we got the x coordinates and the y coordinates. Now, in order to plot, we would need to write it back as a coordinate. So A prime would be 4 6, B prime 2, negative 4, and C prime, negative 6, 2, which is exactly what we have here. So all we would need to do is to plot this, and we can all plot this on our graph, right? We can all find 4, 6,
Yes, sir.
2, negative
sir.
4, and so on. So this is what it would look like with the center of enlargement being at the origin. So this is a triangle, and it's being enlarged. So A, B, and C would be our vertices. A prime, B prime, C prime would be our enlarged vertices. So that is how we tackle enlargement matrix. We would simply need to multiply the vector, the matrix given by the scale factor. And that's it for matrix enlargement. However, another way, so remember the first slide which I had for enlargement matrix. What if we wanted to use this scale factor of 2? What if we wanted to write it as a matrix? How do we write it? This scale factor of 2.
2, 0, 0, 2.
2, 0, 0, 2. Very good. So this here would represent the enlargement matrix. And another way we could get the result is by using the enlargement matrix to multiply our matrix. Now that would be a more tedious process, but in some cases you will have to use that method of finding what you were asked for. So as you can see here, we can use enlargement matrix to multiply the object to get the same result. And as you can see, 2 times 2 plus 0 times 3, 2 times 1 plus 0 times negative 2, and so on and so forth. And we would get the same result as if we simply multiply the given matrix in vertex form as by 2. And that's it for enlargement matrix. Any questions?
Hold on a
No,
little.
sir.
Sir,
Yes.
when we use the enlarged matrix, I see you have in the second bracket, I see you have 2 plus 0. Oh, how did you get that, sir?
All right, so this question actually skipped a step. What happens here is that when we're multiplying, we multiply a row by column. So this first row will be used to multiply this first column. And so we would say 2 times 2, which would give us 4, plus 0 times 3, which would give us 0. So that's how they got it. So after we're finished with that, we would move on to the next column. 2 times 1 gives us 2. 0 times negative 2 gives us 0. So once we're finished with that column, we'll move on to the next column. 2 times negative 3 gives us negative 6. 0 times 1 gives us 0. And after we're finished with the row 1, multiplying all the columns, we would need to move to row 2.
Okay.
So move to row 2, and same process would be applied.
0 times 2.
0
give
times
us
2 gives us 0. 2
and
times
6.
3 gives us the 6. 0 times that gives us 0. 2 times negative 2, that
4.
gives us
Negative 4.
negative 4. Well, it's plus negative 4, even though it's fine. Let me just put it as they have it. So it's plus negative 4. And 0 times negative 3 is 0. 2 times 1, 2. And then when we combine all of this, we would get our result down here. So
4.
clear on that?
Yes, sir. 4, 6, 2, 4, 6, 2. Okay.
All right, good. So any other questions?
Sir, excuse me a bit.
Go ahead. You have a question? All right, so I'm not hearing. All right, so who can guess what comes next? So we did translation, enlargement. What comes next?
Reflection.
Reflection.
It was an easy guess. So we will be looking at reflection matrix. And I have 3 questions for you here. How do you reflect an object? Is that the only way we can reflect? And do you know of any matrix that can be used to reflect an object? So let's start with the easy question. How do you reflect an object?
With the mirror line.
So reflect through the mirror line. Anything else? All right, so is that the only way we can reflect through the mirror line? And do you know of any matrix that can be used to reflect an object? Now, this would be fairly new to you, so I would forgive you if you don't know of any matrix that can be used to reflect an
Sir,
object. Go ahead.
would it be an identity matrix?
Identity matrix. Okay. So give me an example of that.
What? So the coordinates of the object times itself. Although that would be never mind.
Well, it's close because we have 1001 and reflection matrices aren't far off. The different types of matrix that we use aren't far off from the identity matrix. Now, the reason why it can't be an identity matrix is because it would give back the original position which we are reflecting. And if we reflect over a mirror line, we can't get back the same position, right? So there has to be a little bit of change to the matrix that we're used to reflecting. But it's very similar to the identity matrix 1001 and reflection. All right, so we'll review what was said in the video in a bit, but let's look at what's happening here. So a reflection matrix is a matrix that creates a mirror image by reflecting each vertex over a specified line of symmetry. Now to reflect across the y-axis, we multiply the coordinate by the matrix -1, 0, 0, 1. Now, was any of you here last week?
Yes, sir. I was here, sir.
All right, so we looked at reflection and we looked at what would happen in the y-axis. Now, if we have X and Y here, if we're moving an X value, so let's say we had this point at 5, 0, 5, 0. Let's say we wanted to reflect in the y-axis. The point would be somewhere over here, but what would the coordinates of this point be?
Sir,
Yes.
sir, can you repeat, sir? You're breaking up, sir.
All right, so we have this coordinate. So let's just call this A. And the coordinates of A would be 5, 0. We want to reflect in the y-axis to get A prime. What would the coordinates of A prime be if we're reflecting through the y-axis?
-5, 0.
-5, 0. So what do we notice about these coordinates?
Oh, the sign change.
So the sign changes.
Yes, sir.
So remember, earlier when we were establishing our vertex matrices, the first row here represents the x coordinates, right?
Yes, sir.
And the second row represents the y coordinates. Now, what do we notice in the x coordinate? What is that?
It's -1.
So
-1.
So there's a -1 in the x coordinate. Now, this -1 is saying to us that whatever x values we have in our vertex matrix, those x values would change sign. So if we had a -10, it would change to a +10. If we had a 15, it would change to a -15. And what do we have in the y coordinate here?
Positive.
+1.
So this is saying whatever is in the y coordinate stays the same. So this is a simple concept that is taking place here. So it's not a complex thing to say, all right, so we have a 2x2 matrix. What should we do now? The main idea is that we need to recall what happens when we reflect in the y-axis. So what happens when we reflect in the y = x axis? So let's say we have our graph, we had our y = x line.
So the coordinates switch place and the signs change.
Sure.
Yes, sir. That's what you said last week.
So remember, there are two of them, you know. We have the y = x and y = -x.
Coordinates remain the same.
So something happens with the coordinates switching, but what about the sign?
Why?
Sign.
What happens with the sign?
They remain equal the same.
So they would be
The same.
the same.
They remain the same.
Yeah, so the signs would remain the same, however they switch
Yes, sir.
place.
It would remain the same.
So the x would now become the y, and the y would become the x. So who can tell me what the unit matrix is? Someone, we were talking about it earlier and someone brought it up. So what was the unit matrix again?
Unit. Is it the
As
0, 2, 0?
1.
a square matrix with 1.
0,
Sorry, the identity matrix. Sorry about that.
1, 0, 1.
1, 0, 0, 1. So now, so let's say we're looking at this from the coordinate plane, and this is representing our object 1, 0, 0, 1. And if we're going to reflect it in the line y = x, where we said the values of the x and y switch position, right?
Yes, sir.
Now, using this, what would happen is that we would shift our x and y coordinates. So we notice we have a 1 in the, so this is x, this is y. And we realize that we have a 1 in the x position, right?
Yes, sir.
What would happen is that we would switch it to the y position. We have a 1 in the y position, we would switch it to the x position. So what would we get now as our new matrix?
0,
0, sir. 0, 1.
and
1, 0.
0.
So
Yes,
this
sir.
now would be the matrix if we're reflecting over the line y = x. And as such, all of them can be derived using the same concept. So you can just play around with these, the identity matrix, and the concept of reflecting in the various lines, the y-axis, the x-axis, negative y = -x, or the y = x-axis. So there are four main ones that we will encounter in today's session. So just stay tuned for that. So matrix multiplication is not commutative, so be sure to keep the transformation matrix on the left. So don't put the transformation matrix after. So if we're given, let's say 1, 3, 3, 4, and we want to reflect this. So don't go ahead and put the transformation matrix after -1, 0, 0, -1, because matrix multiplication is not commutative. So this will give a different answer than what we would get if we were to put the transformation matrix. Okay. So are we clear on that? So remember,
Yes, sir.
the transformation matrix on the left. Right. So let's look at a question. Did someone say something?
Yes, I was just asking what you said before.
Yeah, I'm saying matrix multiplication is not commutative, so we can't switch the order. So you know, like how addition would be commutative, it does not matter the order in which we add. For matrix multiplication, it's not commutative, so we'd have to put the transformation matrix to the front of the operation taking place. So as an example here, the one being shown in red would be our transformation matrix. So we have to put it in front of the vertex matrix. Clear?
Yes, sir.
All right, so this one says we're required to reflect triangle PQR with coordinates P being 2, 2, Q being 2, -1, and R being 4, 3 across the y-axis. Now, we're going to need to have a recollection of the various transformation matrices for reflection. So across the y-axis, across the x-axis, across the y equal x, and across the y equals -x. Now remember we said that when we reflect across the y-axis, the x values would change sign, right?
Yes, sir.
And the y values would remain the same. So it might look a bit scary here, seeing it in red and as a 2 by 2 matrix. But what will happen is that everything in the first row here represents our x coordinates. Everything in the second row represents the y coordinates. And we could just take a shortcut and say, all right, all the x values will change sign. So we're going to just multiply all the x values by -1. So -1 times 2 gives us -2. -1 times 2 again, -2. -1 times 4, -4. And all the y values will remain the same. So that's just multiplying by 1. So that's just a shortcut to this, right? So if we wanted to go the long route, what we would have to do is to actually carry out this multiplication. I know it's very tedious to perform this multiplication the long way.
So the long way would be column, row by column.
Yes. So I'm going to show you what it is. So it's here on the next page. Actually what it would look like if we were to go about performing the multiplication of the row by column. Now you'd need to have an understanding of this. In most cases, Miss Brian, in most cases, these questions are about 1 mark. So to find the new vertex matrix of the image. So they would go about multiplying by 1 negative. It all depends on which axis it would be reflected in. So this is the procedure to go about doing matrix multiplication. All right, so this is the solution to this question. We have PQR P prime, Q prime, R prime would just, as you can see, be reflected in the y-axis. The distance from P to the line of the mirror line. So from P to the mirror line is just 2 spaces. From P prime to the mirror line, also 2 spaces. So that indicates to us that that is where the mirror line is, the y-axis, and it was already indicated to us.
Yes, sir.
All right, so even though I showed you for a second there, what would happen if we reflect across the x-axis this time? So we reflected across the y-axis and the x values changed sign. So what would happen if we reflected across the x-axis?
So the y-axis will change.
Yes, the y values would change sign. So can you tell me what that matrix would look like?
1, 0, 0, negative 1.
1, 0, 0, negative 1. All right, so it's similar to the reflecting across the y-axis. The only difference is that the signs change. So to reflect a figure across the x-axis, we multiply by 1, 0, 0, negative 1. Or we could perform the shortcut and just multiply everything in row 1 by 1, everything in row 2 by negative 1, which is what is done down here. So if we're required to reflect triangle JKL with coordinates 3, 4, 4, 2, and 1, negative 2 across the x-axis, we're required to find the vertices of the image and graph the diagram, graph and label the diagram. So as I've stated, we could simply use the value here, which is telling us that, okay, all the x values remains the same. However, the y values will be multiplied by negative 1. So our x values are always in the first row here. So 3, 4, 1 represents the vertices of our triangle, or the x coordinates of those vertices. And 4, 2, negative 2 represents the y coordinates of those vertices. Now, if we want to perform this reflection in the x-axis, the x values stay the same, so we would need to just multiply by 1. So 3, 4, 1 would give us our new x coordinates. So this here would be the image, object, and this is our reflection matrix in the x-axis. And the y values would be multiplied by negative 1. So 4 times negative 1 gives us a negative 4. 2 times negative 1, negative 2. And negative 1 times negative 2 gives us a positive 2. So that is how they came about getting those values for the image. Yes.
But sir,
Yes.
can you go back to the, all right, but the negative 2 is the
Yeah,
negative,
change the sign. So whatever was there, just want to see a number being multiplied by negative, it will be the opposite sign.
Positive. Okay, sir.
So if it was a negative number, so let's say negative 5, so if we have positive 5 and negative 5, and we multiply this by negative 1 by negative 1, the sign will change. So this negative 5 will be a positive 5, this positive 5, negative
become
5.
a negative 5.
Okay, so whatever the sign was, it will change to the opposite sign.
Okay, sir.
And let's look at what this actually looks like on our graph. So JKL would be our object, JKL, while J prime, K prime, L prime would be our image. And the coordinates are given here, which we established around here. So there are 2 ways to find the coordinates. We could perform the multiplication the long way, or we could just multiply it across. So x coordinates with the x coordinate of the given vertex or reflection matrix rather. So we have one question for reflection, but first, so quickly take a screenshot of this.
Coordinates.
So quickly take a screenshot of this. So this represents the various matrices that you will encounter. So reflection over the x-axis, reflection over the y-axis, reflection over y equals x, and reflection over y equals negative x. So just quickly take a screenshot of this to see, to keep track of where we are. So you got it?
Yes, sir.
All right, so one quick past paper question. And we'll look at the last type of transformation for the day, which is rotation. So this one says a transformation T represented by the matrix 0, 1, 1, 0 maps S. So the coordinates of S are given 2, 5 onto S prime 5, 2. Describe fully the single transformation T. So this should take you about 2 seconds to look at it and identify what is happening here. So quickly, what is this reflection? What is
Y equal
Huh? Yeah, you can direct with him. Come take this.
We're not on the line graph, not in graph. You know, see what on Tuesday.
all right? So go ahead. What is the transformation that is taking place here? So if we look on the coordinates, we can, what do we see for the coordinates here?
They are similar, sir.
So what changes? So we have 2, 5 and 5, 2. What changes?
the position.
So the x changes with the y, right?
Yes, sir.
So which reflection or which line do we reflect in when the x changes with the y?
Y equal X.
Yes. And they gave us this matrix, and this matrix already indicates to us that we are reflecting in the line y equals x. So how do we describe this transformation? What would we write as our sentence? We could say this represents,
Yes, sir.
yes, a reflection in which line?
Y.
X.
In the line y equals
Y equal x.
yes, because the x and the y coordinates are switching. So this is x, this is y. Now this is x and y. So we realize that the y coordinate switch with x. So we are and this is a graphical representation of it, the line y equal x. So yeah, that is the basics of reflection. And our next type of transformation that we'll be looking at is rotation. Now, rotation is the one that is tricky. Now, the others are pretty basic, but rotation is a bit trickier than the rest. So I need you to pay keen attention for the last part of this session. We just have about 9 more pages, 9 more or 8 more slides to go to get through rotation. But we have a quick video to watch.
Agree with you.
Yeah, because it's at it has to do with the unit circle and trigonometry. It's more advanced.
Okay, sir.
Yeah, but I just need you to focus on the different types of matrices that we use to rotate. Now there are 4 main ones. We'll get to them shortly. Now a rotation matrix is a matrix that is used to rotate a figure. Obvious. That's the stating the obvious. A single matrix can be used to determine the rotation matrix. However, plus and minus must be indicated for accurate calculation. So here we have a general form for the rotation matrix. So let me rewrite this. So this is R being equal to cos theta sine theta negative sine theta and cos. All right, so theta here would represent our angle. So theta, so this means theta, and it is Greek for angle measure. First time hearing it or seeing it?
Yes, sir. First time hearing it.
First time hearing it, sir.
So we all know how to use cos and sine on our calculator, right?
Yes, sir.
So a quick way we could find the different matrices is, for example, let's say we wanted to rotate 90 degrees counterclockwise. So it would just be a positive 90 degree. So what I want you to put on your calculator is cos 90, sine 90, negative sine 90, and cos 90. So what do you get?
So you would get
0, sir.
So cos 90 is 0. So let's just fill in 0 where we have cos 90. What about the negative sine 90 and sine 90?
Sine 90 would have been 1.
So sine 90 is 1. So negative sine 90 is?
-1, sir.
1.
So this here represents a rotation of 90 degrees. So if you are able to recall, or let's say, so this is very important. So if you're able to recall this general form for the rotation, then you'll be able to find the rotation matrix for all of them. So rotation of 180, rotation of 270, 360, it does not matter. All you'd have to do is to just replace theta with whichever angle is given. And remember, if it is anti-clockwise, it's positive. Clockwise, you would use negative. So if we wanted to do a negative 90 degree angle, you know that would be, or a clockwise rotation of 90 degree would be a negative 90 in that case. So once you're able to recall, so just make a jotting of this, the general form for rotation. So let's say general form. And from this, we can find the other rotation matrix. So let me know when you have that written down. Got it?
Yes, sir.
All right, so there are three things that must be known whenever we're performing a rotation. So we must know the direction of turn, the angle of rotation, and the center of rotation. Now, positive 90 degrees will give a counterclockwise rotation, while negative 90 will give a clockwise rotation. Let's see. So just make a note of this. So 90 degrees, counterclockwise rotation, negative 90, clockwise rotation. So if theta, so this is theta, is positive, then we have a counterclockwise rotation. If theta is negative, we have a clockwise rotation. So that's just the basis that we need to remember. Positive, counterclockwise, negative, clockwise. So it's kind of like if we're looking at the watch, we know that clockwise would be the right direction that is going, right? However, in this case, we're looking at the opposite. So if we have a negative, we go clockwise. If we have a positive, we go counterclockwise.
Sir, excuse me, sir. Can you go back to the slide before, sir, please?
Okay, no, this one?
Yes, sir. Thank you, sir.
You're welcome. So here we have it again. So we're looking at two-dimensional rotation. So 2D objects. So the image here is equal to the matrix multiplied by the vertex of the object. So it's similar to what we've been doing. We simply need to multiply by the rotation matrix. And here, they're showing us that the image, so this is the image, and this here is a rotation matrix. And this is the object. So the rotation matrix times the object gives us the image, and so on. So it's very similar to the others. Translation matrix by the times the object gives us the image. Enlargement matrix by the object gives us the image, and so on and so forth. So remember, this is the general form for the rotation matrix. With this, we can find all the other rotation matrices. Now let's look at what they actually are. So we have a rotation of 90 degree, rotation of 180, rotation of 270, and rotation of 360. So quickly take a note of this, as we will be using it to do an example on the next page, which will wrap up our session. Well, we actually have two examples. So make a note of these matrices. So a quick screenshot will do, or if you're writing, that would even be better. Finish?
Yes, sir. No, sir. Let me write stuff real quick.
Got it?
Yes, sir.
All right. So we're given a question here, and we're going to use the rotation matrix to rotate the figure. So use each matrix to rotate the polygon ABCD with the coordinates A being 0, 1, B 2, -4, C 5, 1, and D 2, 3. about the origin. So for this, well, this is your homework, but I want you to tell me what the image will be. What will it be rotated by? So we have the given rotation matrix, and I want you to tell me what it would be rotated by, if it is counterclockwise or if it is...
It would be rotated by 90 degree clockwise.
Is it clockwise or counterclockwise?
Counterclockwise.
I'm hearing clockwise, I'm hearing counterclockwise.
Clockwise, sir.
All right, so some is saying clockwise, some is saying counterclockwise. Which is it?
Counterclockwise.
Counterclockwise.
Why would you say it's counterclockwise?
Because it is positive.
What is positive?
Very nice, man. The next
The degree is positive.
All right, so you said the degree is positive. How do you know the degree is positive, by the way? Okay, Marshall, I'll go back after a second, after I go through this. So remember, what was the general form that we needed to recall?
Cos theta, negative sine theta, and sine theta, cos theta.
All right, so in order to get 0, -1, 1, 0, we know that it's 90 degree based on the layout, but we need to know if it is actually clockwise or counterclockwise. And you said it is counterclockwise because it is positive, right? So if theta is positive 90, so let's just put a plus 90. It would definitely give us 0, -1, 1, 0. Now, what if theta was a -90? What would we get?
+1, -1, 0.
So let me put my thing here. What would we get?
A +1, -1, 0.
Sure, put it on a calculator and let me and tell me. So if theta is cos -90 gives us
-1.
cos -90 is -1.
Hold on a minute. That's 90. 0, sir.
So it's 0. What is negative sine -90?
1.
1. And sine -90?
-1.
-1. And then, of course, this is 0 again. So this would be a rotation of 90 degree clockwise. So when the angle is negative, we are going clockwise. When the angle is positive, we're going anti-clockwise. So just keep that in mind. So remember, the operation is performed on the matrix as, so as you can see here, the X and Y coordinates flip and they also change sign. So then again, the next part of this question will ask us to rotate the polygon or look at what is taking place here and determine the describe the image. So we established earlier that it was a negative 90 degree would give us 0, 1, negative 1, 0, 0, 1, negative 1, 0. So once you're able to identify the rotation matrix, you're good to go. So this has a little bit of trial and error to it. Once you're able to identify the rotation matrix, then you'll be able to describe the types of transformation taking place. I really wish I had some more past paper questions here, but I guess you can find some online to try. And most of these questions is just to describe the transformation that's taking place. So someone was asking me to go back to this slide. So Marshall, quickly take a screenshot, or if you're writing it. So let me know when you have it. All right, so this here is rotated 90 degrees clockwise, and we all know how to reverse engineer the rotation matrix, right?
Not necessarily, sir.
Where did I lose you?
No, it's not, sir. I'm looking at the thing now.
Mm-hmm.
And for the rotation matrix, the 0, 1, negative 1, 0.
Yes.
With the coordinates. This is the same that we're going to multiply the 1 with the 2.
Yeah, that's the long way out. So we would multiply 0 times 0 plus 1 times 1, 0 times 2 plus 1 times negative 4, and so on until we get our image over here.
Okay.
So I guess that is the ideal way to see. So if we're just given, because in this case, we're not just multiplying the 1 times everything here, because as you can see here, in the first row we have 1, negative 4, 1, 3.
Yes, sir. That's what I'm looking at. I'm saying this is gonna be confused because
Yeah, and I realize that's where the issue is at for you. So let's look at it. So for this one, what changes? So if we look closely, we can inspect that the X and Y coordinates switch position, right? We see that. So the X and Y coordinates switches position.
Mm. Oh, from the image, sir.
So this is the object. So the 0 here switches to the 1, switches with the 1. The 2 switches with the negative 4. 5 switches with the 1. 2 switches with the 3. But it does not only switch position, you know. So as you can see here, it switches position, then it is the sign change. So two things taking place there. Switch position, then the sign change. However, the sign, when it switches up to the X coordinate, so this is the X. And this is the Y coordinates. So the X and Y coordinates switch position. However, in this case, so this is a rotation of 90 degrees clockwise. So let's say 90-degree clockwise would be somewhere under here. So the X and Y coordinates would switch position. However, the Y coordinates would be the opposite sign. As you can see below the X axis, so going down here, the Y coordinates would have a negative sign, right? Down here would be negative Y. So that's kind of like the explanation as to what is taking place here. But the key idea behind this is to have an understanding of the different rotation matrices that you will encounter. So the four main ones, and these four main matrices are for all positive angles. And you know, if we change it to a negative angle, something will happen for some of them. So just bear that in mind. I know it's a lot to recall, but if you're able to recall the general form for the rotation matrix, then you should be able to find all other forms of rotation matrices, right?
So the general form is this, sir, the zero.
So it's cos theta, negative sine theta, cos theta.
Okay,
so once you're able to recall that, then you should be able to find the other rotation matrices from that.
Cos theta, negative sine theta,
Sine theta and cos theta. And remember, if the question is rotating,
so is it negative, sir?
Repeat.
The bottom part.
No, it's just cos theta. So cos theta in the top left and cos theta in the bottom right.
Okay, sir.
And remember, if it's rotating clockwise, then you will use a negative angle. If it's rotating counterclockwise or anti-clockwise, you will use a positive angle. All right, so any questions on rotation?
It's negative.
Yes, the angle is negative. Rotating counterclockwise, the angle is positive.
Counterclock angle is positive.